All right. Good evening. We are now down to about 3.5, 4 days to go through and complete putting together our presentation and then submitting it for the NFL 2025 Big Data Bowl. The goal here is to predict post-snap outcomes from information that you have available to you pre-snap. One of the key things here is that it's pretty open-ended in terms of how you want to approach this problem or even describe what you're doing within the data. It's not that you necessarily have to be able to highly accurately predict run versus pass, but it's more about talking about things that are actually actionable and practical, or things that are novel from the data set itself. So they give some examples of things that you could do, like run versus pass, route combinations, which we've done a little bit of work on. But the idea is to come up with something creative and not be tied to trying to predict a certain outcome and keep testing against the holdout set that they're using. So across our different sessions, we had done data exploration, put together a very basic model. Then we worked to expand upon that model. Once we started or stopped getting as much lift in the metrics that we had here, we shifted over to then working on trying to predict route combinations. What we found there was it's actually really challenging to predict the route combinations correctly. There's a lot of correlation between the different route combinations in a play. If you want to think about it, there are certain pairs combinations that work well together, whether it's to attack a defense that you're up against to create an advantage for your offense, or it's just the randomness within the game itself that made that challenging. And then we took some of the fields that we had generated as part of those route combinations and put them back into our run versus pass models to see if that had helped. And basically, we ended up at about the same prediction percentage, not really getting any increase in the information gained from knowing more information about what the defense was doing, as that was a focus for us, improving the route combinations to try and get them to perform better. It didn't particularly help there. And then when we brought that back to the run versus pass, surprisingly, that didn't help all that much either. The goal for today was to go to pull out some of the coefficients from that logistic regression model and see what the key predictors are in the data set to significantly, or see what is significantly predicting certain things. Like if there's a field that is just heavily outweighing the others, we should go down to that. Like we'd seen in our first very basic version, we had just the offense formation, the team that had the ball, and then what was their receiver alignment. And 3 pieces of information gave us a 70% accuracy in the data. And then we've added a number of fields to it as well, and we didn't get that much lift in our prediction. We had gone from 70 to about 75%. One of the surprising things was knowing the players on the play actually caused the model to perform worse. In general, the only places where we were getting some improvement was the random forest model, but then it becomes much more challenging to actually understand how it's coming to the conclusions that it's doing. So the big, shocking takeaway there was that knowing who the players are on the field doesn't actually help improve model performance. It actually causes it to perform worse. So the goal here today is we're going to actually look at those coefficients and see how they are interacting with one another and seeing if there are certain things that we can pull out. Another idea was to look at specific teams and build models for those teams individually. So that way we could see, for example, if there were certain offenses that were very predictable, that we would know basically run versus pass. And we had seen, looking at the data for, I think it was Tampa Bay, one of the things that had caused their run offense to be so poor was that they only ran out of a single back formation. They very rarely ran out of shotgun. for the most part, or sorry, they very rarely passed of the single back formation. It was almost always run. So then defenses would know to key in on run once or twice a game. I think the most we'd see was like 4 times in a game. They had thrown from that single back formation. That was what was allowing defenses to understand them better. So I was curious if we broke down even individual teams once we know those coefficients to see if that helps us to get better models as well. So let's start breaking this down. I know this is still going through and running everything. Every time we come back to this, kind of have to restart the kernel. So building things up from scratch here. Hopefully, if you've been in these previous sessions, you kind of know the general gist of this on how we are breaking down the data. And the idea that we've also generated some fields. So if there was motion by a single player, making that across all the players on that given play, how we merge together the data. So that way we didn't just have who was the quarterback or the running back in the case of a rushing play, who had the receiving yards, and then offensive formation and game situation information, things like the quarters, downs, yards to go, the game clock, the score, and then we create a score differential, and then the yards to go until they score. This here is the part where we talked about who the players are on a given play. Once we had pulled those in, we ended up putting them together. We ended up finding out that that's not actually helping really in any of the models, with the exception of that random forest, where it boosted it by about a percentage point. We also did the same thing for the defensive players, just in a little bit of a different way. Instead of looking at the individual players, we grouped them by their positions that they were playing. So things like cornerback, defensive back, cornerback, safety for the defensive backs, free safeties, and then things like the linebackers, inside, outside linebackers. And what we ended up finding out is that it didn't particularly help us in terms of the knowing the route combinations. And then when we pulled that back into our run versus pass, it didn't cause any lift in the performance there as well. So then these were some of the first visualizations that we put together, just getting an idea of the formation percentage by team. As I looked at this more, this is what led me to believe that maybe if we pull out the different teams, we may get better performance, or by building models for each of the individual teams, we may get better performance in terms of predicting run versus pass, and then maybe even those route combinations as well. And then laying out the offensive performances as you go. So you can kind of see that these are all positively correlated to one another. So as you would expect, if you have a better pass offense, you're also going to have a better rush offense, and then the inverse is also true. So you want to be here in the upper right-hand section and stay away from the lower left-hand section. This was our very first model. This is where we talked about just knowing who the team was, the offensive formation, and the receiver alignment. One of the things I'm curious about here is that once we go and put in the coefficient information, or once we understand the coefficient information, if this is the biggest predictor in terms of run versus pass, or the combination of these two, then by pulling out each team individually, we should start to see some of those other factors, or some of those other variables become larger factors within the model. So you can see here just 3 pieces of information, about 70%, a little over 70% accuracy. And then, like I said, we added in more fields. So making sure the score differential, creating buckets. Sometimes it helped, sometimes it didn't, depending on the model. So just treating the yards to go, sometimes you got better performance. And then other times when you're using this bucket of short, medium, long, you got better performance on models. So yards to go was generally better across the models. But in some cases with the logistic model, it was better to have these as buckets. As we're going through here, we made it another time bucket that I thought was a little bit interesting to pull out, because I know teams treat those final 2 minutes, whether it's of the game or before the half, differently. The reason is that in the case of the end of the game is over. So your strategy has to be completely different as you're running out of time. But also in this halftime 2-minute warning, it's a chance if you're down to put some points on the board before going into the second half, or if you're up to extend that lead. But the clock is also working against you in these cases, because if you run out of time, then you essentially turn the ball over, whether it's you're kicking the ball whether you're getting the ball in the second half or if you're kicking it to the other team. You're essentially starting over at that point. So you want to get those plays in. And that's why you see here this halftime 2-minute warning, where there's 762 plays in this 2-minute window. If you think about it, there's only 13,000 plays across all 60 minutes. So for most of them to fall into this little 2-minute window, or a large portion of them to fall into this 2-minute window, it doesn't match up with other parts of the game as well. And then comparing this against the final 2-minute warning, what I saw here is that there's actually less plays compared to the halftime. And the reason for this is pretty simple, is that if you're up by 2 scores and can just seal the game by running the ball a few times, then you're going to do that. If you are the defense and the game is out of line, you'll call those timeouts quickly, but then you won't be able to stop the clock anymore. And if you're down by 2 touchdowns, you likely had chances doing that anyway. So then as soon as they convert that first down and you don't have 3 timeouts anymore, you're unable to ensure that you get the ball back. So that's why you see more plays run in this 2-minute period right before the half than you do before the end of the game. So we incorporated those additional game situation fields into our models. And we got up to 74% accuracy. And then surprisingly, once I pulled in the players, it actually decreased slightly here. So we went down from 74.1 down to 73.9. It's a small decrease, but when you consider all the different work that has to go into creating all these additional fields, it's typically not worth it. And you also see that even larger when we get to the random forest model, where it goes from taking about 2 minutes to 5 to 10 minutes to do the models once we have all the players in. And then this is what I was talking about, where sometimes it's okay to have the bucket, sometimes it isn't. When we didn't bucket the yards to go and treated them as a number, same thing with the go-to-go, then we got 74.4% accuracy. So like I said, creeping right up on the 75% point. And then when you treated those as numbers and you included the players, the difference became, or the players actually took even more away from the predictive power, as now it's down to 73.8%. Random forests, just want to cover it here. It's harder to show those coefficients to know exactly how the model is predicting what it is. And the challenge here is that the more information you feed it, the better it does. But like I said, it becomes harder and harder to tell what it is actually doing as far as splitting the data into those different forests. So it becomes harder for you to actually use this in a way if you were like a coach. Trying to have an analytics team say, we fit this model, but it's really challenging to say, well, it's like you've got 30 seconds to adjust to what the defense is doing, even less when they finally set. So then how useful is that information? How timely is that information? Again, just 35 seconds here in the basic version of it. And then once we get to the point of including all the players, it gets much longer. Same thing here for the SVM. The situation here is if we have the players, we get about a 2.5 percentage point lift, but it's still, like I said, roughly the same as the random forest. It's a little bit easier to explain or work back to an explanation of why it's predicting what it predicts. But overall, it's just more challenging in terms of, it's not as powerful as those other 2 models were, so you wouldn't take that trade-off. Then we worked on the route predictions. First things that we were doing here was trying to actually add information about the defenses and then more information about the offense itself. So instead of using the player IDs, let's see if maybe it was more useful to know like who the pass catchers or how many pass catchers were available on a play. And it turns out it didn't particularly help us all that much. Same thing for the defense and knowing of how the defense not necessarily is situated in terms of where they are on the field, but the number of players that they have out here. And so including all that in the models, I'll just kind of skip past this here. We put that into the logistic regression model. We could predict about 30% accuracy what the route was going to be. On a given play, there are typically 4 receivers that are out in routes. And so this means like we're getting 1, maybe 2 of those, like rarely getting 2 of those. So it's not that useful in terms of being able to understand the routes that the offense is running. And what this helps us to see is that a lot of times it's predicting only a few of the classes here and then the others far less. So you can see in some of these numbers where it's predicting wheel route 0% of the time because it rarely sees it in the data. You see here, like it did it twice, predicted wheel, and it was actually flat routes most of the time, so I never got it right. And then you go here to the go route, and you can see I got it right 614 times, but it missed on more than that in the group. So we saw the go route 1065, and so it got it right 600 times, but got it wrong over 1,000 times. Not great in terms of its predictive accuracy or helpfulness. So even when it was right, it was mostly just because it was guessing heavily into a few categories and hoping that it would get those right. Very similar thing here happened for the random forest. You can see kind of these heavy differences between the precision and recall scores means that it's not doing great in terms of predicting classes. In fact, in some cases, it's heavily predicting one class versus another. And so it's the same information all over again. So then we included the defenders and the players, thinking, well, maybe this will be more helpful to the model. And it actually decreased our accuracy, again, including players versus just knowing like the number of defenders and number of pass catchers. So there's too much here once you one-hot encode for all the players in a given field that it's too disparate. It may be worthwhile to try and fit the players to individual positions, so you'll know who the quarterback is on the play, because in the case of a pass, there has to be a drop back, and so that would be the quarterback of a given play. Even if they are not officially a quarterback on the roster, they're the one throwing the ball. And then you could try and figure out by their positions, filling in some of the other ones, so who are the wide receivers or tight ends. But again, while you're reducing the size of those subgroups, instead of all players being eligible to be player 1, you might say that this is QB, and so only really QBs or the throwers of the play could be that one. And then same thing for player 2, 3, etc. So that might help increase the accuracy. But generally, from what we're seeing, is that knowing who the offensive players are in terms of the individual players, it does not add much in terms of the predictive power. So there's probably players who are key individually, but the other ones just kind of drown out and create too much noise there. And then same thing, once we did this to the random forests, it actually got much worse this time, knowing the players. Once it had all the defensive information, we dropped below 20% accuracy here. We were at like 28% before. And so losing like 50% of your predictive power is enormous. And so really points to not needing to know who, not really knowing who is or what information is right in terms of the players. We also added a fourth model to here. It's called decision trees. What this does is it will split the data at certain points once it meets a certain threshold. So, for example, we could say one of the cutoffs, and this is chosen at random, is that yards to go is greater than 5, and that is where it splits the data. So everything that is greater than 5 goes to one side, everything that's less than 5 goes to the other, and then it keeps making those splits. So now, if we are focusing on this side with the greater than 5 yards, it will find some value that creates the best split in the data after that and splits that group more. And then the same thing on this side where we're at the less than 5 side. If there is a factor of, let's say, a certain team, it will bring that one group out and leave the rest of them in a group as it meets the information. And then it continues working over until it reaches the depth that you had set. In this case, I had built one that tried all the combinations 5 through 50. So letting it split 5 times, letting it split 50 times. What you see here is around 23, 24 times. You stop gaining any predictive accuracy. So it's not worth it to continue on. And you can actually see here right away at 5 was the best outcome for the model. And then this shows the results here. So just letting it split 5 times, let it get to 31% accuracy. As you let it split more and more times, it was actually getting worse from that point. You do see a dip here below to that 19 percentage points, and then it works its way back up and stabilizes at 22%. So you do have that in the data. There will always be kind of almost a wave pattern, unless there are very few but very strong predictive patterns. And then the nice thing about a decision tree is that you can get exactly what rules it was using to predict the data. So this is looking at how it split the data. You can see here it predicts a wide variety of classes, but there are only a few that it actually gets right. So you can see here it had trouble predicting angle versus flat. So it confused those two routes in particular between them highly. And then you can see here, these were the ones, if you go kind of diagonally this way, of predicting correctly. So again, 30% accuracy, not really that great. Again, if you think about it, there are on average about four receivers running out on a play. So being able to predict one route correctly, not that great or useful. And then these are the rules split out. So the NFL ID was the person who was actually going to be the receiver on the given play. So it said there was the very first split it could do is that if it was this player, it would pull all their data to one side, and then the other side of the tree was the rest of the data. And then it did that again a few times. So the most useful information was that it knew certain players only ran certain routes. And then it pulled those out. But because this group is so large that it becomes very challenging for the model to really predict well beyond that. Because it's, let's say this one, I think we had let it go 8 times in here. Let's just double check that real quick. No, this was 43. It was using a lot of those splits to just pull out singular players rather than focus on, like you can see here, the first time it pulled in some factor was when the receiver alignment was a 2x2. And then you can see here, knowing that there were 2 wide receivers in a 2x2 provided predictive power. And then here you go, the score differential, right? Starts to come in. And then now you can see, oh, the defending team was Kansas City. But the thing here is that allowing it to split so many times, it focused on pulling out individual players to improve its accuracy rather than looking for larger breaks in terms of the data. And then this is the illustration of that tree. I won't really go into it, but you can see here how, like I said, we pulled out certain players all the way through until you come down to this side. But these are allowed to go down 40 in depth, but they never particularly do. So even though it was allowed to go that, and that's why you see in the data set, it evened out at a point where it wasn't gaining any more predictive power. And that's because there were no more ways for it to actually split the data set to gain information. And like I said, we came back to the run versus pass data set, bringing in those new fields that we had generated in terms of the offensive pass catchers and the defense to try and see if those had actually led us any additional predictive power. And what we saw is that it's basically the same. So 74.4% accuracy here in terms of the logistic model. And you can see how it's breaking these down. So it's about evenly split between them in terms of the ways that it misses. And then it's a little bit uneven in terms of when we looked at this in the decision tree model, we let it go around 25 deep, which is not the best. We just gave it a random number here. What we see here is that it misses quite a bit more than the other one. So we could get a better idea on the split if we went back and fed it through all the different versions of it again. It does not take particularly long in terms of predicting run versus pass. So we can work through that pretty quickly. But again, we're talking here 60, in this case, yeah, about 60% accuracy. So 2 out of 3 times it'll be right, and the other time it'll be wrong. So coming back to here, what I wanted to do was to work through here and begin to pull out the factors in this so we can know which ones are affecting it. So the way to do this is we want to get the model and its steps. And the way to do this, let's just call this the logistic regression model. And we're pulling a log model from right above here. And we are going to get the steps. And this is a classifier. And another thing we need to do here is because we did the pre-processing, we want to know the steps that did as well. So this is basically how it made all the different groups, especially for the one-hot encoding. So we want log model, and then we want the same thing be named steps. And this is that pre-processing step. Pre-processor. Once we have those, we want to pull out the features. So there are the categorical and the variable, or the numerical, right? We see cat and number. So we want to just pull out the categorical features. And what we want to do then is we want to go to the preprocessor that we just made. The named transformers. We call those cat. And then get feature names. Getting the categorical variables. And then we need to do the same thing for numeric. So we're going to go, and there's nothing to really pull out. We're just going to pull the numeric variables from before. Then we're going to combine them together into a set. So we're going to take the list of categorical features. And we're simply going to add numeric. I'm just going to add numeric variables. I don't think we need this. If we had some transformation going on, it would be worth it, but let's not. So categorical features is here, and then numeric variables from up here. Great. So it's going to take a second. Maybe it's this way. Let's separate these into 2 steps just to make sure we got it working right. That part's no problem. One hot folder has no attribute get feature names. Out. There we go. Okay. So that takes care of that. And then we want to get our coefficients. So we want to take that, just a regression model, OF, and then 0. And the same thing, we want the intercepts. So we're going to do the same thing, logistic, regression, and intercepts. Got those. Boom. And then we're going to combine these into the data frame just so we can put them together side by side. So let's just call this log UDF. We want to take a data frame. Oops. We want features. So I guess I should say feature. All features. And then coefficient. Coefficients. Do that the same. Let's just double check this. Here. Perfect. Okay. And one of the other things here, so I should share this out. This is the Big Data Bowl data set to work from, and then I'll share out the GitHub as well. Because I've been sharing the notebooks with the updates there as well. So I have the coefficients. And I do want to back here, sort the values by coefficient so they should be decreasing as we go. Now if I look at log df, where does that intercepts? So it starts with a negative value and then works its way up. I didn't do the sorting here. Oh, it's the absolute value of those. Got it. Okay. So it did sort it. But positive and negative here. So knowing it's a empty formation actually decreased its accuracy, but then like off when it knows wildcat, it increases. There's going to be groups here knowing, for example, Chicago was a positive relationship, knowing shotgun was a negative relationship. So it seems like there are some formations that are good and bad. I want to see if I can see the whole data frame. If I put a print around this, will it show me the whole thing? I want to look at it in. No. Well, we can always visualize it. Start here. Let's sort it, but not on the absolute value, just doing the regular one. So let's go log TF, sort values by coefficient. And then sending is still false. And then let's start building this out. So we'll use a bar plot. I want to show feature. And then the coefficient. Okay, I will do those the same. Do in this case, the x should be the coefficient. This should be coefficient. Give it a moment. I'll check the chats for questions. That's ugly. It does not actually help us. Yeah, there's so many here that it's not representative. There are a few that are wildly negative and wildly positive. Like we had seen up here, right? We see those negative ones. Where am I? Where'd it go? Anyway, some of these are such heavily negative coefficients that it makes it empty backfield, harder for it to predict correctly. But if it's wildcat, much easier. And then there's a few others that are in that same group as well. I think what we're seeing here is there's a good amount here in the middle where there is literally zero predictive power. Working through those, it's so what do we see? There's certain information that doesn't particularly help us. Knowing that there's a single inside linebacker is not useful. Knowing it's Detroit or New England, receiver alignment here. Knowing quarterback is not, or sorry, not knowing that it's quarter number 3 isn't helpful to the model. Like really either positively or negatively. We're talking about fractions of fractions at this point. So there may be things that we can remove to better know what's happening here. So let's look at okay, so none of these were particularly. I'm trying to think. So it was helpful knowing Chicago was a team, but then there were times where knowing that it's New England or Detroit, it wasn't actually helpful knowing those offenses. I want to see like the first. Can it show me the first 10 rows? Okay. So motion since line set, not a number. That shouldn't be in the data. It should either be 0 or 1. So there's an issue with that. But when it isn't, it's still a positive predictor. What else do we see? Knowing 4 cornerbacks is a negative coefficient in terms of correctly predicting. Same thing with knowing that there are 4 safeties. There's going to be some correlation in between these because we're going purely off of the player's assigned position. But if you're thinking about nickel formations, or in this case having like 4 free safeties, it's probably dime, like 10 defensive backs. That those two are linked. But either way, it's negative in terms of helping our prediction, knowing that information. But it seems like there are certain formations that are very influential in terms of influencing the model. So if I split the models on formations, we should get better predictive information by doing that. So I suppose I should have arranged these better. And a few rows here, and I'm just going to move this information up. It's not interfering with what we are, or we're not interfering with what we're doing here. Up, and then the classification report. So take that out. Now that we have all this working, let's collapse this down. Got the coefficients. So if I go, what is the data set that we're using here? Rush def data. So, body count. We got Python series value counts. Value counts. So if I do this and I do unique, so I want to make one for each version of the offense formation. So then let's start here. Oops. I want that there. I want this. So offense formation comes out of the categorical variables here. And the same thing. What is going on? Comes out of there and comes out of here. So then I want, just call this single back. Let's pull this out, actually make sure this works correctly. So single back equals rush def data. Sorry. Offense formation equal single back. I think it works this way. Perfect. So this will be the only thing that's changing. This goes to here. And then instead of using the rush defender data, everything becomes single back. And then we go through creating the regression model. And then so let's experiment. So when we train it on just the single back grouping, let's do this. Let's pull that value count back just so we know how many rows we're working with. So single back, there are 3,500 rows total. And then saying that we have 20% of that left over. So about what, 700 rows. And that's roughly what we're seeing here. What it's doing is basically predicting run every time, even if it's not that case. So single back formation, it's always saying that there's a run you're going to get. That's why you see this group being so large, even though it's not actually true. So it predicted run, but it was likely to be passed. So what this means is that there are a lot of teams that will only run from the single back formation. Very rare for them to pass the ball. And so that's why we're seeing that outcome here. If we just go print right, what do we get? 78% accuracy, just by always predicting yes. Very rarely do you have something else that you would want to predict no, even then, and this is at 50-50. Right, so here's a case where it predicted pass 84 times total across that group, and it was right 44% of time, or 44 out of those 84 times, and the other times it was wrong. So, like I said, about 50% accuracy once it's actually doing it or predicting pass. So it's better off just predicting rush every time, right? Because then you would get these 40 and then do the same thing. So I guess this shouldn't be shocking. We do know that there are a lot of teams that will run only from that single back formation, and that's why we're seeing it here. And then the other group that I was curious about was the shotgun formation, as there was a greater variety for teams in that. So we'll go here. We will call this shotgun. Go here. Oops. Thanks. Copy. Paste. Paste. Shotgun. That would probably be a very similar situation. So shotgun here predicting pass majority of the time, and it would be, I guess, fairly less accurate than before, but still fairly accurate in doing so. It's probably going to be what, around 60 or so % of the time. Yeah, 2/3 of the time. That's right. Where you're basically, you know that it's shotgun formation, right? We've held that out from the model. Even giving it all the other information, it's just going to 67% of the time predict that. And then if let's do this here, see if we can improve the accuracy. We're going to remove all that offensive information. Same thing here. We're going to know whether rush versus pass. Remember, we were 67% before. About the same, 66%. So here, knowing the offensive information improved it very slightly, but not enough to make a large difference in terms of the single back, or sorry, the shotgun formation, and I would expect very much the same thing for single back. So adding a lot of overhead in terms of computing out the additional columns to not really gain a whole lot in terms of the predictive power. So let's do a few examples here. So instead of splitting by the offense formation, we're going to just do a team abbreviation. It should be roughly the same in terms of the value counts here, but you can see they're roughly near one another. So then if I do, instead of this one being single back, I'm going to call this one TB. Going through, doing TB here. And what you see here is fairly high accuracy, 76%, where it's a team like Tampa Bay where we were pretty clear looking at the data that they only ran from certain formations. Even still, the model's only at 76% accuracy with those. And we're including all that defensive information as well. So knowing how many receivers they have on the field, tight ends, running backs, all that same information. And then let's add in a few more. We're going to go back and we're going to look at the pulling out this information here. So now that we have that, paste it in here. Right, we're going to get the log model. We're going to get its steps. We're going to get the data frame. And then let's just look. We'll look at the top 10 factors for it here. So when it was a 3x2 formation, it was less and decreased the likelihood of the coefficient. Interestingly enough, here halftime 2-minute warning also decreased the accuracy in terms of prediction. Knowing that it was first down improved things. No tight ends also caused a decrease here. So that's more wide receivers and running backs. Whether there was motion or there wasn't motion was a heavy predictor here, or heavily influenced it. So when there was motion, decreased the likelihood of being able to know this. What this means is that the quarterback likely saw something with the defense and made changes to it enough to make the model less accurate. But then if there was no movement, it was more correct. The model was more correct in making its assumption based off the other information here. So it's a 2 percentage point swing across whether there was motion or not, right? Something very binary in terms of it. And then you can see here if there were like 3 defensive tackles, more predictable. Also, if it was Dallas, being able to predict correctly more often. So, I don't know, can we take this out to 20 even? Yeah. Much more fall in as we kind of approach towards zero, towards this. Third down, they became less predictable. Same thing for fourth down. Receiver alignment. If it's a 1-by-1, it's more likely to know who or what's happening here. One of the things that jumped out to me is I would have expected the offensive formation to have jumped out here a bit more in terms of the predictive power. I'm kind of surprised that it's not here in like the top 20 factors, as that was something that when I looked at it, I thought that would be a bigger predictor in terms of how they are breaking down their offensive selections. So what we're seeing here is that the offensive and defensive information is there. So maybe that is a substitute for the offensive formation. So let's go back to here. And I'm going to remove those from the Tampa Bay model here. If we go here, and let's get those top factors. Oh, I don't think formation's in the model, right? Yeah, it's not. So that was I forgot to add that back in after we changed the team abbreviation. So mistake on my part. Offensive formation. Oh, all right. There, that's the model I get. %81 accuracy now. So being able to go and fit to specific teams has dramatically improved the accuracy here. So right, we were struggling to get above 75%. Now we're at 81%. And then if we look at the top factors, I'm sure here, there we go. Offensive formation. But then there are ones that are very heavily improving the model here as well. It looks like a few times, like defensive teams, it seems like New Orleans was very predictable in terms of their offense versus when they went against KC, less predictable. Interestingly enough here, first down, they were more predictable, and then in the later downs, less so. We see this again here. When they are in motion, they become less predictable as an offense versus when there is no motion on the play. It's easier for the model to predict. Again, that's about a 2 percentage point swings across those. You can see they also will act differently on the score differential. So they change their approach based on the difference in the scores in the game. Interestingly enough, the time bucket here. So when there's no, when it's like not the, you can see here the halftime 2-minute warning, they become less predictable. When it's not that time, they become far more predictable. Then let's see, yards to go becomes less predictable as that decreases because that's a numeric. Sorry, as it increases, it becomes less predictable. So what this means is that if it's like 1 or 2 yards to go, that's less of a negative influence. But then as you get out to like 10 yards for first down, they are less predictable, if I'm understanding that correctly. And then here's that motion since line set is 0. Interesting. So there are a fair amount of Nana numbers, which I didn't believe should have been possible based on the way I set that up. But it's there. So we do see pulling out certain teams had influenced our model here. So that was pulling out Tampa Bay. Oh, let's go back quickly. That was the shotgun version. Because I thought these were clouding out the offensive formation info here. Let's just put these back in for Tampa and see if that helps or changes any of the factors that are going on. So actually decreased the accuracy. We're just straight 80% here. What this means is that it's adding more confusion into the model. You can see here, it's not particularly helping in the top factors. Once we get down further, that's when they start to come in more, but it's not, a lot of these will kind of negate one another in terms of their predictive help. So it does create confusion then. Let's see if we have that for just the offensive factors or offensive players. And the nice thing is this is a logistic model, so it's much quicker to iterate on. If this was the random forest, we'd have to go, wait 5 minutes for this to go through again and again. So logistic model here is coming out nicely in terms of helping us iterate quickly at this point in time. So here we go. Knowing the offensive players actually helps the model increase about a whole percentage point more. Even though it's not one of the top factors here, something in it helped to improve the model performance. So that was interesting. So we know the defending team, a few times they showed up here, like when it was KC, that was less predictable. Dallas, more predictable. New Orleans, more predictable. Atlanta, less predictable. So defending team is a factor one way or the other, and so that helps the model quite a bit. Knowing the downs helps the model as well. So this gets interesting here. Like, we're starting to hit a point we really can't break down the models further than this. Like, if I wanted to fit a model for Tampa in the single back, right? Hold those two factors true in our data set, it would get far too small. Like, we saw that back here when we saw Tampa Bay has 424 plays that they ran over the course of the season. And we're holding out 20% for our data set, which is that group of 80. But to break this down more into the specific formations, we're now like too small to be reliably predicting for our data set. And there's too many other factors that would be making those like smaller models way less stable in terms of their predictions. So we saw here, knowing that it's Tampa, we get like 82% model accuracy, which is better than the 75% that we were having before. So like being able to hold out single pieces of information is great. what we saw when we tried to break down the two largest offensive formations, both the shotgun and the single back, we actually got worse model accuracy that way. So it doesn't help holding the formations constant. Seems like teams then use these much differently depending on what the team is. So then next time when we come back, we will I'll put together a function we'll go through each of the teams basically and pull out their predictive models, their accuracies, and then trying to do these confusion matrix for each of them. So we get an idea of how this pulls together. We'll also get an idea of like which teams are, let's call them more complex in terms of prediction versus less. We did do some experimentation here with Tampa. Removing the defensive information actually helped the model. We went from 81% to 82%. So knowing the defender's specific information was not helpful to the model, introduced some confusion. So we can work through those as well. Another thing I need to look into is this motion since line set. For some reason, it should have been 0 or 1, but we saw not a number in the data set here. So I need to go back and see what's happening in those scenarios. So we'll pick that up for next time. That's all for today. I think this was a useful session. We're kind of building towards what we want the key insights to be here. I think focusing in on these offensive formation and receiver alignments, we see that the offensive formations, the models weren't as predictive when we broke down by that, but when we broke down by the team, we started to get a lot more powerful models. I'd be curious. I want to pull all the teams to see which are the less predictable of those teams in terms of their offense. I know Tampa was one that was a little bit easier to break down based on the formations. We'd seen that just looking through it. So I want to see if that holds true for a lot of the other teams as well. And then we can conclude that we want to get above that 75% accuracy across all the teams, or we can say that there are a few teams that are, there must be a better way to break that team down. So that's all for today. I know we're coming up on the deadline. I will be live again tomorrow to continue here. Like I said, we'll work through how to pull all of the teams together as a group, and then pull all the teams out of them and group their data, and then look at the accuracy of those models and see if we can get it so that every team is above 75% in terms of the accuracy, and we'll work through those ones on breaking it down. So tomorrow will probably be a little bit of a longer session overall, because we'll have a lot more ways we'll have to go through each team to figure this out. Like we had worked on Tampa, removing the defenders. So I'll give it all the information that we'd had at the beginning. And then for each team that isn't already above 75%, we'll break those down even more. So that's all for today. Thank you for watching this. We'll only have a few videos left in this series before we have to end it because of the competition deadlines. And then I'll share the findings that I put together for that as well. So if you're seeing this, thank you. Please leave a comment in the video on anything that you found interesting or that you want to see. Even after the competition ends, we can always come back and revisit some of these because we have the data sets saved here. So that way we can better leverage them or reuse them and look into some other things that we find here after the fact. So thank you all for coming. Have a great day, and I will see you all again tomorrow.